All right, the first problem out of the two that I'm going to do is from number 8 on worksheet 36X, tension practice. And in this particular case, you have a frictionless environment, so mu equals 0 between the 2m block and the surface. And of course, we're also given the information that m equals 1 kilogram, and also force F, which does not apply in this case, is 10. But again, that does not apply in this particular case. Drawing a free body diagram for each of these, I'm going to call this object 1, this object 2, and this object 3. So for object 1, the free body diagram looks like this. We have, of course, the force of gravity of object 1 acting down. We have in the upward direction the normal force, and we know that the force of gravity equals mass, which is 2m times acceleration due to gravity. And since there's no acceleration in the up or down direction, normal force must be equal in magnitude to that. In the horizontal direction, we have tension that's acting like this. And I'm going to call this tension 1, since there will be another tension that will be found in the string down between m and 3m down in here. So this tension 1 describes the force exerted by the string on mass 2m. All right, for object 2, mass m here, we have the following forces acting on it. We have tension 1 acting in the upward direction. And this is the Newton's third law force pair to this tension 1. So these two forces are equal in magnitude. And then, of course, there's the weight, or the force of gravity, for object 2, acting down. And that's equal to the object's mass, m, times g. And there's also a tension acting in the downward direction from this string, that rope. And so I'll point that down, tension 2, we'll call that. And so we have those three forces acting on object 2. And then to object 3, a free body diagram for that. We have tension 2 in the upward direction. This is the Newton's third law force pair to that tension 2. And in the downward direction, we have the force of gravity for object 3. And that's equal to the object's mass, which is 3m, times the acceleration due to gravity, g. All right, so I'm going to describe sort of a one-dimensional system here, where I'm going to call this the positive direction, that the positive direction, and that the negative direction. So when the pulley twists from our perspective in a clockwise direction, that is going to move the whole system in the positive direction, and when it's turning in the counterclockwise direction, it's going to move the whole system in a negative direction. So keeping that in mind, for object 1, what we really care about is the sum of the forces, and I'll write it like this: sum of the forces parallel to the direction of motion. So that those parallel lines refer to the forces parallel to the direction of motion, equals the object's mass, which is 2m, times its acceleration, a. Object 2, for object 2, we have sum of the forces on object 2 parallel to motion equals the mass of object 2, which is m, times acceleration a. And for object 3, the sum of the forces in the parallel to motion direction on object 3 equals object 3's mass, which is 3m times its acceleration. Now this acceleration a is the same acceleration in all cases, since the system is constrained by the ropes tying each mass together. They're all going to accelerate at the same rate. So those are all the same variables there. So if I go and list these through, what are the forces parallel to motion in the on the object 1? And so for that, we just have the tension 1 up here, and that's acting in the positive direction. So we have tension 1, which equals 2m. Well, m is just 1 kilogram, so equals 2 times a. So we have one equation, two variables, cannot solve. For object 2, we have in the direction parallel to motion, we have three forces. We have in the positive direction, remember positive is down here. In the positive direction, we have both tension 2, which we don't know, the force of gravity 2 is also in the positive direction, and we have tension 1 in the negative direction, equals mass times acceleration in the direction of motion. And for object 3, we have in the direction of motion, we have two forces parallel to the direction of motion. We have in the positive direction, the force of gravity on object 3. And in the negative direction, we have tension 2. And that equals the object's mass times acceleration. Well, let's fill in some other numbers regarding what we know here. I can calculate both the force of gravity on object 2 and the force of gravity on object 3, since the force of gravity of object 2 is this equal to m, which is 1 kilogram, times g, which is 9.8. That equals 9.8 newtons. And similarly, force of gravity in object 3 is 3 times m. M is 1. So 3 kilograms times 9.8 meters per second squared. And for that, we get 29.4 newtons. And so I can plug in 29.4 newtons there. So continuing on here for object 3, we do not know tension 2. We do know that m equals 1, so 3 times a. So I have, in this particular equation, I have two unknowns. And backing up to object 2 here, we don't know T2. We do know force of gravity on object 2 is 9.8 newtons. We don't know T1. We do know that m is 1, and then a. So there we have three unknowns. And then in the case of object 1, we have both of these variables that we do not know, T1 and A. So we right now have three equations and three unknowns. And so we have a system of equations, and we can play our algebraic games here to solve for each of these. We want to know the tension in each case, and we want to know the acceleration. So if we solve for T2 over on this side, T2 equals 29.4, subtract 3a, and we can now use this in place of T2 over here. So this now becomes, in place of T2, we have all of this. So 29.4 subtract 3a plus 9.8 subtract T1 equals a. Well, I can play one more substitution game here and replace T1 with this term up here. When I do that, we get 29.4, subtract 3a plus 9.8, subtract 2a equals a. Now, if we combine like terms, we end up getting, you can solve for a and get 6.53 meters per second squared for the acceleration. Once you know the acceleration, it's one of the things you're looking for, you can now plug that in for this a and this a, since they're all accelerating at the same rate, and solve for both t1 and t2, and you should get t1 so this t1 equals 13 newtons, and t2 then, you plug in the value for a, t2 equals 9.81 newtons. So that's what you're looking for. The acceleration of the system, 6.53 meters per second squared in the positive direction. So it's going in the positive direction like this and increasing in speed. And then the tension T1 is 13 newtons. So this mass is being pulled 13 newtons that direction. This mass is being pulled by 13 newtons that direction. And tension 2, which is in here, pulling each direction, is the 9.81 newtons.